Okay, so let's talk about what waves are and some basic characteristics of waves. This unit is going to be more vocabulary heavy. There's a lot of new terms to learn, but on the plus side, it's less math heavy. In fact, you've basically gotten through the most difficult math heavy unit of the course, which is circuits. So congratulate yourself. From here on out, we're learning more about descriptions of things, things you could sort of draw in a diagram and explain, with some calculations rather than heavy calculations using lots of equations together. So look forward to that. So here are some things that waves have in common. In order for something to be considered a wave, something needs to be traveling, and that is energy and also information. These are things that can be sort of transmitted from place to place. A good example of a wave transmitting information is Wi-Fi. Your phone gets information about the internet from the Wi-Fi router in the room. And a good example of waves transmitting energy is something like light waves. Okay. It's important that we realize it's not an actual object that is traveling. So if we kicked a soccer ball, this is not a wave. This is not a great soccer ball either, but it's definitely not a wave, and it might not be a soccer ball. So if we kick something like a soccer ball, that's not a wave, that's just an actual object that's traveling. This object has mass. So a wave generally does not transfer mass. And anything that meets this criteria of transferring energy or information but not mass can be considered a wave. Now, it's important to realize mass can move around a little bit while a wave is being transferred or while a wave is moving, but it's not moving together with the wave the entire distance from start to finish. So we'll investigate that a little more closely. So some examples. You can wiggle one end of a slinky and it moves to the other end. We have light is a wave, sound is a wave. When we think about hearing sound, here I'm talking and my phone is picking up the vibrations through the air. It's moving from my mouth to the phone microphone through the air, and that's carrying both energy and information. And in this case, the information that it's carrying is the words that I'm saying. Things like radio waves, ocean waves. Some examples of things that are not waves. Wind I wouldn't consider a wave because wind can cause ocean waves, but that's actually the entire air mass moving. So the actual stuff is moving from place to place. Kicking a ball is not a wave. I don't know, driving in a car, anything that's something actually moving from start to finish would not really be considered a wave. So waves have things we can measure. Lowercase v still stands for velocity, and its units are still meters per second. A can stand for amplitude, and it's basically how strong the disturbance is. And the units for amplitude could be different depending on the type of wave. So you won't have to do too much with actually calculating amplitude, but you might need to be able to read it off a graph. And in that case, it's dependent on the type of wave what the units would be. F is frequency. It's how often the wave repeats. And the units are a special unit, hertz, which means cycles per second. So just like something like newtons is a unit made out of other units, hertz is a derived unit. It's made out of units of seconds. It's a number per second. T is the period, or the length of time that each cycle takes, and so the units are the normal units of time, which are seconds. And then this special letter, lambda, it looks like an upside down letter Y, but it's a Greek letter lambda. Which is kind of like the Greek version of the letter L. So even though it looks like an upside down Y, it stands for length, and this is the wavelength, which is how big the wave is, distance from beginning to end of one complete cycle of the wave. So let me try to illustrate some of these things a little bit with making some waves in this chain. So if I wiggle one side of the chain, you can see that the disturbance moves along the chain. It's not perfect because it's got some friction on the paper. But we can see that when I move one side, it creates a disturbance that moves across the chain. So we can measure how fast does that disturbance move. We could measure how big was the disturbance. Did I move it a lot, or did I move it just a little bit? I can measure how often it repeats. Am I doing a motion that's slow, or am I doing a motion that repeats faster? Frequency and period are closely related. They're both related to how often the wave repeats, and we'll look into that a little more on the next page. And then the wavelength would basically be how wide is the disturbance in the chain. And with this particular setup, it's a little bit hard to see that. But I'll try to find something that shows it a little more clearly for next time. Okay. So if we look at this graph of a wave, let's point out some of these characteristics the best that we can. This is sort of its normal resting position, would be wherever the middle is. And so then from that, how far away from that resting position do we get would be the amplitude. It's important to realize the amplitude is from the middle to the top and not from the bottom to the top. This from here to here would give us double the amplitude that we're actually looking for. In this case, the amplitude would be 0.8 centimeters based on the scale and based on the label that I see here. We can also label a period. I can see that I have the lowest point here at 3 seconds and again at 7 seconds. That's a difference of 4 seconds, which is going to be 1 period. To measure the period, you can measure from 1 top value to the next top value, in this case that'd be 1 second to 5 seconds, you can measure from one bottom value to the next bottom value. It's important that you don't just go, here's the middle, here it is at the middle again. The period is from 4 to 6, so that would be 2 seconds. In between this point and this point, we only have half of a cycle. Whereas from here to here, we have 1 full cycle. So the period here would be 4 seconds. And if we think about, we have 1 wave in 4 seconds. We want to know how many waves per second. So in 4 seconds, we have 1 entire wave. How many waves do we get per second? 1/4. Every second that goes by, we have 1/4 of this full cycle passing by. So hopefully this lets you see that there's a relationship between the frequency, this is how many waves per second, and the period, how many seconds per wave. That relationship is T equals 1 over F, or F equals 1 over T. T is the period, and F is the frequency. Only one of these is on the reference table. I think it's this one, but you can use either one. They really mean the same thing, whichever one's more convenient. So if 4 cycles were to go by in 1 second, that means that the frequency is 4 hertz. 1 second is about this fast. So 4 cycles in 1 second would be 4 times that speed. Like, that's about 4 hertz, because that's 4 little ticks every second. The period would be how long does each wave last. If I get 4 waves going by every second, then each wave lasts for 0.25 or 1/4 seconds. We could take this 4 hertz and put it in the equation. It's always that 1 over relationship. If it takes 3 seconds for half of 1 cycle, what's the frequency, what's the period? So 3 seconds go by and we're watching this wave go by and it's only done half of its cycle. That means that the period would need to be 6 seconds for the entire wave to go by. You could think about period as seconds, but it's really seconds per wave. And the frequency is waves per second, or cycles per second. So number of waves that we have is 0.5 waves per 3 seconds, and that's going to be 1/6 hertz, or 0.166 repeating hertz. So if the period is 6 seconds, the frequency is 0.1667. If a period is 0.2 seconds, or 0.02 seconds, sorry, what is the frequency? So this means a wave goes by really quickly. In just 0.02 seconds, it's gone through 1 whole cycle. And then we want to know how many of those cycles can we get to happen in 1 second. And we can use the equation F equals 1 over t. In this case, it's 1 over 0.02 seconds. And that's going to give us an answer of 50 hertz. Cool. All right. Let's do a little bit more, and I'm going through a lot here, about types of waves. So we can basically ask two different questions. Does the disturbance have a repeating pattern? If the answer is no, we would call that a pulse wave. It's just a single disturbance that's traveling. It's not a repeating cycle. It's just kind of like a snap. And it can have amplitude, but it doesn't have a frequency because it's not repeating. So we can't say how many cycles per second did it have. If the disturbance does have a repeating pattern, we call it a periodic wave. It's usually shaped like a sine wave, which looks like this. But any repeating pattern is periodic, so it could look like something like that. And it has a defined frequency / period. Okay, so that's one of the two main questions that we can ask to categorize a wave. The other one is what the disturbance is doing compared to the direction of travel. If it's in the same direction, we call it a longitudinal wave. And the disturbance creates compressions or rarefactions. So I'm going to try to draw a slinky here. When it's talking about the direction of travel, think about holding on to the end of a slinky. And then what's the disturbance doing? If you take the end of the slinky and you shake it in this direction along the slinky, you will create a a longitudinal wave. So I'm going to try to draw a slinky of what it would look like when it has a longitudinal wave moving through it. Hopefully you can see that it's kind of alternating between areas where it's more scrunched up and areas where it's more spread out. So this is called a compression. This is called a rarefaction. It's kind of a weird word. If something is rare, there's not very much of it. So this is the area where it's more spread out. And then a wavelength is one entire cycle, meaning it includes one compression and one rarefaction. So I'm looking at the end of this compression and then the end of this compression. This would be one wavelength. So we can do this with a slinky. The other big example is sound waves. Are probably the most important longitudinal waves to know about. There are also certain types of earthquake waves that are longitudinal. And a longitudinal wave always needs a medium, meaning material, to travel through. There's a lot of words here, I know. If the disturbance is in the perpendicular direction, so again, we look at a slinky, and now instead of shaking it in this direction along the slinky, we're going to shake it up and down. This is called a transverse wave. So some good examples of this are water waves, technically light, radio waves are transverse waves. Some earthquake waves are also transverse waves. Where we see these crests and troughs that you probably think of as a wave. The longitudinal ones are a little weirder. They're a little bit less familiar, harder to picture. The transverse waves are probably what you picture in your head when you're looking at a wave. This type of thing. Okay. So this is called a crest, where the top is. This is called a trough, where the bottom is. And again, one wavelength is one full cycle. I'm going to use the symbol here for wavelength, lambda, either from a trough to a trough or from a crest to a crest. Those are the easiest places to see that we have exactly one full cycle. Though you could also measure from the middle, but that gets a little bit tricky because you have to be careful that you're looking at one cycle and not half of a cycle. For transverse waves, the disturbance can be in a medium, like a slinky, or it can be in empty space, like a vacuum. So light waves come to us through space from the sun. The sunlight does not travel through any material in between, the sun and entering the Earth's atmosphere. There's not air there for it to move through, but it gets through there anyway. Cool. So here we have we have illustrations of the different types of waves. So A, B, C, and D. Try to figure out what they fall into, whether they are transverse or longitudinal, and whether they are a pulse wave or a periodic wave. This one's a transverse pulse because it's moving up and down, but it's only one little thing, it's not repeating. This is transverse and periodic, meaning it's repeating and it's moving up and down. So this one is longitudinal pulse. We can see we've got just one little compression here, it's not repeating. And this one is longitudinal periodic. Cool. All right. Hope that this made sense to you. It's a lot of new words, but the math is not too bad, and a lot of it is stuff that's easy to physically see and understand how it's working. Hope everybody had a good weekend. I'll talk to you again soon.